Okay, so let's get started. Yeah. So far, in this sorting algorithm section, we have covered three basic sorting algorithms, right? One is insertion sort, and the second one is your bubble sort. Third one is your selection sort. So these three algorithms we have covered so far, and we have seen the worst case time complexity for all these three algorithms is big O of n square, which is not that good, right? So if you have a large data set and if you want to sort the data, then this time complexity is not good, right? So can we reduce it? When we say can we reduce it, that means we cannot reduce it for sure for those algorithms, but can we have a better design or better algorithm, sorting algorithm, which will give us, a lesser time complexity as compared to big O of n square? The answer is yes, we have. Okay, so how can we design better, more efficient sorting algorithms? We'll see in this class. So there is one approach, we can call it as, which is divide and conquer. So this approach was used by Britishers also, right? Uh, you know, during this independence movement. So they used to divide us based on religion, caste, and everything, and then they conquered it, like they ruled us, right? So kind of similar, kind of similar approach we are going to use here, divide and conquer. So we are going to divide the bigger problem into sub problems, and then we will find the solution of the smaller problems to build up this solution for the bigger problem. Okay, you will understand. Let's see here. So let's see the motivation behind this divide and conquer approach. So far we have seen order of n square sorting algorithms. How can we start to do better? So let's assume that it takes t seconds to run insertion sort on the following array. Okay, there is one array given to you and it takes t seconds to run the insertion sort. Okay, fine. Now, can you tell me approximately how many seconds will it take to run insertion sort on each of the following arrays? So now what we have done, if you carefully observe, we had one array. Now we have split it. We have split it into two arrays, two sub arrays, you can say, right? The left part and the right part. Now approximately how many seconds it will take? So let's try to analyze it. When I have an input of n elements, that means an array of n elements, in that case it is taking t seconds, right? But now what do I have? I have two arrays of n by 2 elements. So now if the data size is n by 2, and right, it is taking order of n square insertion sort, it is taking order of n square. Now what about the time complexity here if you have n by 2 elements? So if you just substitute n with n by 2, so you will be getting what? N square by 4. Yes or no? So can we say this, that approximately it will take t by 4 seconds, right? T by 4 seconds for each of the array to sort using insertion sort? Correct. And in total, you can say it will take t by 2 seconds, right? Because you have two arrays, right? One is taking t by 4 seconds, another one is also taking t by 4 seconds. So total time will be t by 2 seconds, right? Okay. So if the answer is each array should only take about t by 4 seconds to sort. That's what we have seen. So what is the main insight here? Sorting n elements directly takes total time t. Sorting two sets of n by 2 elements, that is total of n elements, takes total time t by 2, right? So we got a speed up, right? That means we have reduced the time. So we got a speed up by sorting smaller set of elements at a time. So are you getting the intuition or the idea behind it, what we are trying to do? We are trying to split a larger problem into smaller problems, and then we will find the solution, or then we will basically sort them. Okay. So the main idea behind divide and conquer algorithms is taking advantage of this. Let's design algorithms that break up a problem into many subproblems and that can be solved in parallel. So this divide and conquer method, it's a powerful problem solving technique. Divide and conquer method solves problem in the following steps. So there are two steps basically. One first step is divide. So you are going to divide. That means when I say divide, that means we are going to divide the larger problem into smaller problems and recursively solve these smaller problems. Conquer step is you are going to merge the results. Okay, whatever solution, whatever results you are going to get for the smaller problems, you are going to merge it to produce the result for the larger problem. Understood? So basically one step is divide, second step is join, you can say, or conquer, you can say. Right. So now the one of the algorithms that comes under this approach, divide and conquer, is merge sort. Okay. So as the name suggests, what we are trying to do here, we are trying to merge it. Okay. So let's understand what it is. So first of all, we will understand through example and then we will see the code. Okay. The implementation, how we can implement it. Okay. So merge sort, as I told you just now, it's a divide and conquer sorting algorithm. What you are going to do under the divide step, you are first going to divide the array into two equal halves. Okay. If it is possible to divide into two equal halves, let's say you have 8 elements. So definitely you can divide it into 4 and 4 into two arrays, right? But let's say if you have odd number of elements, 7 or maybe 9, in that case, obviously one array will have one element more than the other array. Okay, but it should be approximately two equal halves. Okay, and then recursively sort the two halves. Okay, and in the conquer step, you are going to merge the two halves to form a sorted array. So you will get more when we proceed further. I'm sorry. Okay, so now in this recursive sorting algorithm, when we are talking about recursion, so definitely there is a base case. There would be a base case where you are going to stop the recursion and there will be one recursive step. So what is this base case here? Carefully say this. The base case here says where we are going to stop when we are going to have an empty or a single element list. Because let's say you have a single element list or let's say empty list. Can I say it is already sorted, right? No element is present in this. Or you have only one element present inside the list. This is also sorted. That means we can stop, right? So that is your base case. So can I say base case can be if length of the list or length of the array basically, if it is less than 2, or you can say it is less than equal to 1. Can I say this is going to be your base case? In that case, you can simply return. Correct. Okay. What will be this recursive step here? Recursive step is very simple. First, you are going to break the list into halves, right? And recursively sort each part. So you are going to basically divide it into half. And then the last step would be to merge, to combine them back to a single sorted list. So basically it's a join. Clear? So let's see here. Let's see the illustration with the example and then it will be very clear to you. Let's say this is the original array given to you or the list given to you. What you do first, you first divide it, right? So you divide it into two halves, done. You further divide it into two halves. So 14 to 9 is here, 7 to 15 is here, 5 to 11 is here, 1 to 4 is here. You further keep on dividing it, 14 to 6, 3, 9, 7, 16, and so on. You further divide it. So you are going to keep on dividing or keep on splitting this sub arrays or sub list until you find a single element list, because there we can stop this splitting further. Why? Because you have a single element in the list and that is already sorted. Is this clear? So far you have seen the division, right? How we are dividing it. Clear? Let's proceed. So what do we do now? When does the sorting magic happen? So we have seen, okay, we have seen that, okay, we have performed the division. Now we are getting the sublist, which is having a single element inside that, right? But how the sorting will happen? To understand the sorting now, you need to understand the core of merge sort, which is merge algorithm. So this is the core of merge sort. Okay, this is the core of merge sort, because everything, most of the thing, or you can say the most important steps would be included in this merge algorithm. So let's try to understand what we are trying to do now. So the key insight is merge here. Let's understand the merge algorithm. So let's say if we have two ordered lists, you have this list and you have a second list also. If you carefully observe, both are sorted already, correct? 1 3 4 5 6 2 5 7 9 10. Now what we are trying to do in this, we will try to combine these two lists to form a single list which is also going to be sorted. Okay, so this is our task. Basically, you can understand, this is our task. This is first we have to accomplish in order to have the merge sort in place. So first we need to understand this. So the bigger list will contain all members of the two lists, and this process is called merging. So how we are going to proceed with this, right? It's very simple. You have all these steps, but I will simply explain you. You can read all these steps later on as well. Whatever I'm going to explain, that is same, that is written over here. Okay, carefully say this. So we have these two lists, 1 and 2. These two lists are there. So one by one, we are going to compare, we are going to iterate over these two lists, and we are going to compare the elements. So we are comparing this first element of this and first element of this. So 1 and 2, which is smaller? 1. So in the new list, you will add this element 1. Now once you add, so you have added 1 from here, that means in the left, let's say, okay, just to make things more easy, uh, just a minute, let me name this as left list and right list. So this is your left and this is your right, and this is your new list. Let's say it is new list. Okay, let's not name it, let's say it is a result. So you compare 1 and 2. 1 is less than 2, so you add it. So oh, just a minute. So you added 1 to new list. Now you are going to, so you have added 1 from here, you are going to proceed further. You are going to increment the value I. So okay, or you are going to increment the index. Now you are going to compare the next element 3 and 2, which is smaller, 2. So you are going to add 2 now to the new list. So you are going to increment it. Now 3 and 5, 3 is lesser, add it, increment it. 4 and 5, 4 is lesser, add it, increment it. 5 and 5. Now carefully see this. With this example, you will understand that why this merge sort algorithm is stable. So 5 and 5, 5 and 5 is comparing, so they are equal, right? So you will add it from the left list. Now you are going to increment it, correct? So the order is also maintained, right, for the duplicate elements. Now 6 and 5, which is smaller? 5 is smaller, so you add it, increment it. Now 6 and 7, 6 is smaller, increment it, I mean add it. Now carefully observe, can I say now the whatever elements that were present in the left list are over? Now the only elements left is in the right sublist, right, or subarray, correct? Now if one of the linked list, the traversal is over, that means if we have finished traversing one of the linked list, the elements present in other linked list will be copied as it is, because they are already sorted. So we have copied it 7 9 10 as it is here. Is this clear? This is what is happening in the merge algorithm. Okay, any doubt so far? Clear, right? Okay, let's proceed. So you can read all these steps, the same thing, everything is mentioned exactly same, whatever I have explained here. The comparison will be there. If one list is empty, so you are going to copy the rest of the elements of the list, other list, in the resultant or the result. So if you carefully observe what we have done one by one comparison, right? Can I say we have traversed over all the, we have traversed over both the lists or both the arrays completely, right? Now, can I say that this merge algorithm will take order of n time, or you can say order of length of left list or left array plus length of right list or left right array, and collectively we can say it is nothing but order of n. If the total number of elements combining both the list is n, so it is going to be order of n. So each steps makes a single comparison and reduces the number of elements by one, right? If there are total n elements, this algorithm will run in order of n time. Fine, let's proceed. So the key insights in this merge, the merge algorithm takes in two sorted lists, combine them into a single sorted list. When both lists are non-empty, compare their first elements, remove the smaller element and append it to the output. Once one list is empty, add all elements from the other list to the output. This is what we have done. Again, the same thing is mentioned, right? Okay. So far, we have seen how we are dividing it, how we are splitting the array, and we also discussed the merge algorithm, which is the core of merge sort, right? Now, how we can use this merge algorithm in this merge sort. Carefully see this. So after the division, after splitting the arrays till we have a single element list, sublist, right? Like this. Now we have to merge. So this is one list, this is one list. Can I say now we can apply this merge algorithm on these two sublist, and it will simply give us what? 6 and 14. Now we are merging it. Okay. So now we are finding the solution for the smaller problems so that we can build up on the, we can build up and find the solution for the larger problem. 3 and 9, no change, this order. 7, 16, 2, 15, 5, 10, 8, 11, 1, 13, 12 and 4. Again, sort. So 4 and 12. So if you remember, in the merge algorithm, we started with two sorted lists. So here also we have all the list as sorted because there is only single element that is already sorted. Further, now we can consider these two as the list because they are already sorted. So if you combine them, if you merge, you will be getting 3, 6, 9, 14. Similarly here, similarly here, similarly here. Again, you will build up on this. You will combine these two lists now. You will be getting another sorted list. These two lists, another sorted list. And finally, you will combine this to get the final array having all the n elements in a sorted manner. This is the illustration for merge sort. This is actually what we are doing. Understood? Now we will see the implementation. We'll see the code, how it is working, and it is very simple. Once you understand how it is, how the things are going on in this algorithm, understanding the code is very easy. So the code here is given in Python so that it will be very easy for you to understand. The code, if you see in other languages also, it is also very similar, right? Just a few changes will be there, rest everything is same. So first of all, as I told you, the core of merge sort is merge algorithm, right? So here we have, first we will see how this merge is happening. That means if you have two sorted lists, how they are merging into forming a single sorted list or array. So you have a function here, define merge left and right. You have provided as an input two sorted lists, right? Left and right. And carefully observe here, you are creating another empty list for result, right? Why this is important? Because you will understand here that we are using some extra space. So if you are using some extra space, can I say the merge algorithm is not in place? Exactly, very good. So merge algorithm is not in place algorithm. By default, it is not, but with slight modifications, we can make it, but it will become very complex. So by default, it is not in place because we use extra space. Okay. So I and j both are 0, initialized to 0 because they are representing the index for both the list, first index. Now carefully see this. While I is less than length of left and j is less than length of right. So till this, if these two conditions satisfies, that means we have the elements present in both the list. Yes or no? Correct. We have the elements present in both the list. None of the list is empty if this condition is true. Okay. So what you are going to do? Very simple. If left of I is less than equal to right of j, comparing the first two elements, first elements of both the list, if it is less, you simply append the result. You simply append into the result left of I, and you will increment I plus 1, right? You will increment I by 1. Else, that means the element present in the right list is smaller. In that case, you will append the right element and you will increment j. Very simple, right? Now, when this condition does not satisfy, when this condition is false, while condition is false, what does that mean? That means either of them, either one of the list is empty. That means, or you have traversed the entire list. Correct? Yes or no? So in that case, you will have to check which of the list is still having the elements inside it. Because if one of the list is empty, for the other list you have to copy the remaining elements as it is. Correct? So if you see here, this one, while I is less than length of left, if this condition is true, what does that mean? What does that mean? That means right array is empty. Or let me use the term array and list, both are similar. So right list is empty if this condition is true. Yes or no? Correct? Because if I is less than length of, that means you have not traversed the entire left list. And if you are coming at this position, that means right list is empty, gone. So what you are going to do, you are going to copy the remaining elements of left list into the result. And what about this thing? If this condition is becoming true, that means left list is empty. Empty means you have traversed whatever elements were there, or maybe it is empty initially also possible. Okay, is this clear? And finally you will return the result. Any doubt in this merge algorithm? This is the key, this is the most important thing here. Rest everything is easy, and this is also easy once you understand it clearly, right? Okay, so let's proceed further. And this merge is going to take order of n time, because we are traversing the entire two lists, right? And total will be order of n. The same thing is mentioned over here. You can give it a read later on. Complexity of merging sublist. Okay, now we come to the merge sort, the main sorting algorithm. So if you carefully observe, see, we have seen the merge step. That means we have seen the last step, correct? So far. Before that, what we need to do, just think about it. We need to simply divide it, right? Can I say you need to simply call it recursively? You need to simply call merge sort recursively before, like after dividing it into half, right? So carefully see this, very simple. Now you have defined merge sort. You are providing one original list or array to this, and you have a base case here. If length of L is less than 2, that means you have either 0 elements in the list or you have only one element. Then in that case, do you really need to sort it out? No, you can simply return that same list over if you have only one element or no elements. Fine. Now, if this is not the case, that means you have more than one element present inside the list. What you need to do, I told you, you need to divide the original list into half. Every time you are going to divide the list into half. So middle you are going to find, which is going to be length of L divided by 2. Correct? You find the middle and you will call this merge sort. So you will call this merge sort now on the left list and the right list, because you have done the division. You have found the middle index basically. Now what you are passing here, you are passing L of, carefully say this. So you have covered Python already, right? This is what From 0 to middle minus 1. If I have something like this, 5, what all elements will be covered? So 0, index 1, index 2, index 3, index 4. Till 4 will be covered. Yes, 0 to 4. But this 5 is not included, right? Now, so what you are doing, you are simply passing the first half of the list to merge sort, and you are calling it recursively. And to the right part, you are passing middle, then column. That means middle is now included till the end, right? Till the end. So now you are also calling it recursively, right? And then after that, you have this merge step. So what will happen? You have original list, divided first into first half, second half. Now, can I say first, this first recursive call will happen? What it will do? It will further find its middle, right? And divide it further, then further middle, divide it further until you get this thing, the base case, when you have less than one element. And then you will start merging, right? You will go to this right part also, right? You will keep on splitting and then you will start merging. This is how this recursion is happening, right? So you will start merging the single element list and then you will build on that. Is this clear? Merge takes order of n work. Now we need to find out what about this merge sort, right? We need to do analysis also. What will be the time complexity of this entire merge sort algorithm, right? So is this clear so far? Do you have any doubt in this? Crystal clear? Okay, good. And the code is also very simple, right? Now, I hope that you can write this code without looking at it also, just now, if you want to. It's not very difficult, right? Okay, let's proceed. So now it's time to do the analysis. We have seen the illustration, we have seen the implementation, you can say, because the code is there, right? And now we will talk about the analysis part. So in merge sort, as I told you, the bulk of work is done in the merge step. That is the core of merge algorithm, merge sort algorithm, which is merge algorithm or merge step. Now the important question is, how many times is this merge called, right? We need to find out that. So carefully say this. See what is happening. Carefully say this. Let me explain you here. You have one list or array of n elements. You divide it first into half. So you get n by 2 elements here. You get n by 2 elements here. Correct. You divide it further. You get n by 4, n by 4 elements of list, n by 4, n by 4. If you divide it further, you will get n by 8, n by 8, and so on. Can I say you will go up to when you have only one element present in the list, in every sublist? So can I say you will go up to n divided by 2 raised to the power k? When the list size becomes this n by 2 raised to power k, it becomes 1. Can I say this? When n by 2 raised to the power k is equal to 1. So now what is k here? Can I say k is the number of levels? You have already seen this thing before, right? If you remember. Correct. In binary search also we have seen this, right? And in trees also we have seen this when we talk about, finding the height of a tree. There also you have seen these concepts, right? So n is nothing but 2 raised to the power k. You take log on both sides and you will be getting k as log n. Yes or no? These many levels are there. Correct? These many levels are there. Now we need to find what? We need to find the amount of work we are doing here. Amount of work at every level. So let's say at level 0. Then we need to find the amount of work we are doing at level 1. Amount of work we are doing at level 2. Right? So if I can find the amount of work I'm doing, on every level, and I know the number of levels also, can I say I can find the total amount of work done on this, right? So this is how we are going to perform the analysis here. So carefully see this. This is a basically this is a tree based analysis. Okay, so so basically, if you remember, right, we have solved few questions finding out the time complexity when you have a code given to you. Yes or no? Then we see the loops and we can find the time complexity, overall time complexity. But this is another approach of finding it. So when we have kind of recursion, so we use this tree based approach to find the total time complexity. And we basically, what we do, we try to find out the amount of work done at every level, and then we find the number of levels, which will give us the total number of, or sorry, total amount work done. Okay, and that is going to be the time complexity. So carefully see this. Level 0, we want to merge sort n items. So can I say one call to merge sort will happen? Initially, only one call on merge sort will happen, right? When you are going to call this main algorithm, you are providing the list, right? At level 1, you have n by 2 items, right? Merge sort n by 2s. So can I say two calls to merge sort will happen? One for this, another for this. Correct. At the next level, 4 calls will happen. 1, 2, 3, 4. For all these lists, 4 calls will be there, 2 raised to power 2 calls. How many levels are there? You have log n levels there. So 2 raised to power log n, 2 raised to power log n is what? You have base as n2 also, right? It is nothing but n. You know the log property. So n calls to the merge sort, because at the last level, at the log n level, the number of elements are n. That means you have n as the sublist at the last level. So n calls to merge sort. Is this clear so far? So we have seen how many calls are there to the merge sort at every level. Now carefully see this. What about the merge function that we are calling? Can I say at level 0 there is no call to merge, because initial original list is there, right? But what about level 1? At level 1 there will be one call with n by 2 items in each half. So n by 2 there, n by 2 in the right? So one calls to merge. So what will be the total amount of work done? Carefully try to understand this, what is happening here. uh, okay, let me explain you here itself. See, I'm talking about this particular level, right? This is level 1, right? You are calling merge. I'm talking about merge now, okay? The main algorithm, not merge sort, merge. You are going to merge these two lists. So one call is there to the merge, one call is there to the merge, and you are applying merge to these two equal halves, these two lists basically, right? Which is of each of size n by 2, each of size n by 2. So can I say that total amount of work done at level 1 is order of n only? Do you agree? Any doubt in this? One merge call is there to merge these two lists, because division is done. Now we are discussing merge. So one call is there for merging these two left and right, and we have two sublists of n by 2 size each. So the total amount of work will be order of n at level 1. Correct. What about level 2? How many? So you need to merge this with this, you need to merge this with this. How many merge calls will be there? Can you tell me now? At level 2, how many merge calls will be there? Just merge calls I'm asking. At level 2, yes, two merge calls will be there. One is to merge these two, and another one is to merge these two. So two merge calls are there, right? Two merge calls are there, and you have, for every merge call, you have two sublists of n by 4 size. Here also, can I say it is going to be order of n, the amount of work done at level 2? Yes. And for here also it is order of n only. Clear? Okay. Now, can I say at every level it is going to be same? Because here also, if you consider, carefully see this, here also it is given. At log n level, what is happening? At log n level, 2 raised to power log n minus 1, which is nothing but n by 2. This is what you are going to get, right? You can write it as 2 raised to power log n divided by 2, and this will give you n only, so n by 2. N by 2 calls will be there at the log n level, calls to merge, right? With n by 2, n divided by 2 raised to power log n, items in each half, that means only one item is there in every sub list. Now if you multiply this n by 2 into 1, still that will give you what? Order of n time. So can I say at every level, the amount of work done is order of n only? Correct? So how many levels you have? Log n levels you have, right? So the total time complexity or total amount of work done will be what? Log n into n, and you will be getting n log n as the time complexity. This is the time complexity for the entire merge sort, right? So basically, if you see here, the same thing is explained over here by visualization, order of n, work done at each level. How many levels are there? Log n level. So I've given you the reasoning why we are getting this order of n, because just by visualization you won't understand, right? But now I've explained this, right? Why we are getting this order of n time amount of work at every level. So we have log n levels, order of log n levels. So the total work done will be n into log n. Now carefully see this. We know this merge is taking order of n work, right? We know the reasoning because one by one comparison is there for the entire list, entire two lists. What about this? This is taking, merge sort is taking order of n log n times. So if you add order of n log n plus n, which is the bigger term? N log n is the bigger term. So the total time complexity will be order of n log n. Is this clear? Any doubt? So can we say it is less than, so in worst case also, basically in every case for merge sort, whether it is best case, average case, worst case, the time complexity is order of n log n only, right? And can we say it is better than the previous three sorting algorithms that we have discussed? The answer is definitely yes. Okay. Any doubt in this so far? Crystal clear? Okay, good. So what are the pros and cons here for merge sort? The pros is the performance is guaranteed. When I say performance is guaranteed, that means in every inverse scenario also it will take order of n log n only, right? Unaffected by the original ordering of the input. If you have an algorithm already sorted, still it will take n log n, right? That was the best case. If you have a reverse, still it will take n log n. It is suitable for extremely large number of inputs, can operate on input portion by portion, that means part by part. These are the pros. What are the cons? Not easy to implement. So do you feel it is not easy to implement? As compared to previous three algorithms, you will say the code is bigger, right? But actually, if you understand it once, you can definitely write the code again, right? Because if you don't understand, then you are going to just mug up the code, and that is not going to help you in the longer run, right? So when it says not easy to implement, that means as compared to the previous sorting algorithm, because that is just few lines of code. But here you have to define the merge function separately, and then you have a merge sort also, right? Which is going to call this merge sort recursively and merge function. Okay. And it requires additional storage during merging operation. So we have seen we are maintaining a result empty list, right, which is going to have the final sorted list. So order of an extra space storage needed. So we can say here that it is not in place. And what about the stability? Is it stable? Yes, it is stable. So in pros, we can say, we can add one or more point here, that yes, it is stable. Any doubt? Stable means the duplicate elements. If you have duplicate elements, the relative order will be maintained even after sorting. Okay. And that's it. So that was your merge algorithm. Now, if you have any doubt, please ask. See, many